Hello everybody. In this video I will try to demonstrate some strong points of the asynchronous instruction and talk about some of the strong points and how to avoid the weak points of it. I am teaching in Math Plus school in Newton, and I found out that I am losing efficiency compared to studying in the room when I have to use Zoom for instruction, because I tend to wave my hands a lot in front of the blackboard and I lose the presentation side of the instructions. So I found out that it's very convenient to use short videos to supplement the instruction, especially before the actual class. It's very easy to send them the link to the YouTube and say, could you please watch this? It worked very well for me for introduction of new ideas. So here are the things that I came up with as general rules of it. First of all, to use asynchronous mode as a scarce resource. So treat it as if you don't have enough of it. So only put the things that are absolutely great in asynchronous mode into it. Things like rewind and repeat. This option is not present in a classroom. You have to erase the board and redo everything. It's quite a bit more convenient when you have a video and you can just rewind. You also can bring things as if a one-on-one instruction. You have an individual watching the screen, so it's just for them. It's quite difficult to go around the class with the same little picture if it's not something on the board. If it's a thing that you have to show, pass it around, you waste time. Here you actually can do quite well. Also, because it's asynchronous, I try to avoid any ambivalence. I try to make the pictures super clear and maybe make them simpler than they should be, just for the sake that I don't introduce any ambivalence, because I'm not there to catch misunderstandings. So these are my basic things, and now I'm going to use a particular example, which I have done in my class, explaining about inverse functions. Because inverse function is a function, you should say something about what the functions are. And there are very many ways to talk about functions, because in classical algebra they could be talked about as a mapping mechanism. You have a set and you map to another set. You could have a function as the common English word, which is very handy because many math words don't actually mean the same thing. Power and energy in physics don't mean the same thing as they mean for humans in everyday life. But a function means the same thing. It's something that does something. So you put in a thing and you get the output from the function. So here's my little handwriting scribble. For example, at the input there is gas, the function is the car, and it gives you travel at the output. You come up to the well, you crank the well crank, and the barrel lifts up the water in the bucket. So the input is you cranking it, the function itself is the crank, the barrel, the rope. The output is the water. A meat grinder is a function. You put meat in the input. Here's a meat grinder. You put meat in the input, you get ground meat at the output. So the meat grinder is a function. It can take an input and it produces the output. So it is a very convenient view of a function, because graphical representation can be used in this exact meaning. The graph can be treated as input and output, and sometimes we forget that we do that. So for example, we can treat a function as having an input side and the output side. The function is the graph, and now let me demonstrate one of the fortes of the asynchronous approach. I can zoom into the picture. We can have a function that's some kind of a curve, and it's actually a machine. You take some place on the input, some point. In this case it's number 6. You go up until you hit the thing, and you go left until you hit the output axis, the y-axis, and I'm overloading my sound. And this is the output, so this is input 1, this is output 1. I took my first point. For every point I can do the same thing. So the curve is itself a machine that lets me take the input and produce the output from it. Because I want to use the best features that are maximized for asynchronous instruction, that's what I'm going to do. I'm going to talk about a function as a machine with input and output, and I'm going to use the graphical representation to present the ideas about the inverse function. Alright, so we know what the function is now. We can now talk about inverse functions. What do they do? The inverse function is a way to bring us back, right? So if the function takes the input and produces the output, the inverse function is a different machine. You can take the output of the first function, stick it in the input of this one, and it gives us the original thing that we put into the first function. It's actually easier to explain with something like an example. So here's my scribble again. So what is useful in the inverse function? What does it? Why do we actually study? Why do we care? Take the time of day. The time of day, if you stick it into a function, it will give you the position of the sun. You can calculate the position of the sun from the time of day. The function is that formula. If you forgot a watch, but you know the formula, you can calculate back. You can figure out what is the function from the position to the sun to the time of day. And then if you forgot the watch, you can recover your time. You grow up somewhere. That's your input. The input is the place where you grow up. You develop an accent, just like I do. You can probably clearly say that I have an accent. The accent is the output of the function. Function itself is, we don't know what, it's time and nature, right? That's what makes you acquire the accent. But somebody could train their ears to recognize accents and develop the inverse function. You listen to the person's accent and you actually recover where they have grown up. So the inverse function is being able to identify where the person grew up from their accent. A function that is the ballistic function, for example. You have a cannon that, and now I should zoom out. You have a cannon that shoots cannonballs at your castle. If you have studied ballistics, then you can calculate the function of where the cannonball is going to land. If you know how heavy it is, if you know what size the bag of powder is that they put in the cannon, and the angle of the cannon to the horizontal. Why is the inverse function important? Because if you knew about cannons and you're in the castle, you managed to recover one of the cannonballs that fell, and you measured the angle that it landed at and the speed that it landed at. Then you went to the scale and you weighed it. You can actually figure out where the cannons are, and you can shoot back and destroy them. So that's one way they're useful. Echo in the cave. Somebody is trapped in the cave. They're shouting at you, but you're at the outside. But the echo is so heavy, so dense, that you cannot actually make out what they're saying. It's very hard to figure out what the words are. So you're about to go save them. You'd like to know what they're shouting. Maybe it's not safe for you to go in. If you knew some sound, for example, a finger snap, right? You could ask them to finger snap, or they could have finger snapped because they knew this. You measure what the echo is because you have a recorder. You now have a function of how an original sound gets transformed into the sound with the echo. You can recalculate the inverse function, and you can use it to recover what they were shouting at you, right? Maybe it was important. Maybe they're asking you not to go and save them because they want to hang around more. So this is why we study the inverse functions. Of course, we use math for it because math models everything. So if we can figure out inverse functions in math, we can figure it out everywhere. So we start with very simple examples. another thing that I have on my cheat sheet here is use very simple examples. So first of all, I referred to general experiences to explain what the inverse function is and why it's helpful. And now I'm going to use something that a person in an algebra class doesn't need help understanding. Say a function is to lift something up by 5 meters. If I put something in, the function is to lift something by 5 meters, right? You add 5 to the position. What's the inverse function? Well, that's very easy. How to get back from there to the original, right? You just lower it. So the inverse function is going to be x minus 5. You start noticing the expression is different for the inverse function. You can also graph it right away. X plus 5 is like that. X minus 5 is there, like that. X, y. So here is my y equals x minus 5, the inverse function. I will call the original function forward function. It's not a real name, but it's like the analog recording. Once we got the digital recording, we have to have a new word to refer to the recording that's not digital, so we call it analog. We have inverse functions here, so I'll refer to the original one as the forward function. So there we go. We can come up with some other easy functions. For example, I'm multiplying by a number. Say I have a recorder here that I use for voice recording, and right there are numbers. So right now my speech is gained by number 9. It's just multiplied by 9. So y equals x times 9. The inverse function. I've multiplied something by 9. I'd like to come back from there, so I need to divide that result by 9, right? Inverse is going to be x multiplied by 1 over 9. It's also easy to graph. Something like that. Y equals 9x. And something like that is y equals x over 9. Clearly it's a different graph, it's a different expression. Well, what's the use of this function? You could recover by the volume of my voice what the volume is set at, right? So for example, I'm talking to you right now. I can bring the volume down. I'm multiplying by a smaller number, 5 now. You can hear it. I'm going back. So by listening to it, you can recover the position of the gain handle here. Right, this is very practical kind of things. At this point, students have studied functions that are more elaborate, so we can do y equals x squared. I squared a number. How do I get back? I take the square root of it, right? Square root of a square is a number itself. So the inverse function is square root of x. We can draw it. I'm not going to be very careful. This is a parabola of some kind. This is a square root of some kind. And we are starting to notice a pattern. And of course this is asynchronous, so you just have to say that the pattern is an inverse function is symmetric to the forward function with respect to the diagonal y equals x. So you go here, you show that it's symmetric, right? You look at this, and even though it doesn't appear symmetric in the very beginning, you can make it look slightly more symmetric. And so that's going to be the premise of the whole following explanation. We've found this symmetry, and we're going to prove that it is in fact symmetric. So right now I'm going into the actual details of the subject matter. So bear with me if you're interested in the inverse functions. I have to become slightly more careful at drawing. So here is my input, which is the x-axis. This is my output, y-axis. And I'm going to examine a random function. Of course, I'm only saying random function. I'm actually going to draw it super carefully because I'm interested in getting a neat drawing that doesn't have details that I don't want. So I have carefully rehearsed how to make this curve. If you look at instructions from good geometry teachers, you will be amazed how they can draw a triangle that's a random triangle. It's not an isosceles, it's not equilateral, all the angles are different, it's not a right triangle. It's actually very hard to draw a good example triangle that doesn't look like something special. So here we are. How does the inverse function work? We have an input. I'll call it input 1. We know how functions work. You go up until you hit the curve. This is my first step. And from there you go left until you hit the y-axis. This is my output. The inverse function is something that when I put the output into it, I get the original input. So I have to copy the output of my forward function to the input side of the picture. I copy it over. As the output of the inverse function, I'm supposed to get this number. What was it? 3, 6, 8.5. So I copy this number to my y side of the picture. And the inverse function, when I put this number which I have copied into it, it will give me this output, right? So I can recover this one point of the inverse function. I know the coordinates of this point because the way I made this drawing, I know where every coordinates are. This is just in 1, out 1 are the coordinates. Because of the way I constructed this point, its input has this number. Input is the first coordinate. Its output has that number, which is the second coordinate. I know the coordinates of this point. I also notice my symmetry again, right? This length is the same as this. This length is the same as this. So it's very clearly symmetric about this axis, about the diagonal. Because I took a random point, in principle, this is true about every point on the inverse function, that it is symmetric to some point on the primary function, the forward function. Well, look at this. What do I know about the inverse function? I know that for every point, if I flip the coordinates, they will satisfy the original function. This is very cool. What does it mean? It means that if I have the equation of the forward function, for example, y equals 5 over 2x plus 3. If I want to figure out what the inverse function is, all I do is I flip the input and output and put it in the original function. So I say, if this is my forward function, x equals 5 over 2y plus 3 is the equation of the inverse function. And look, we see that it at least is not blatantly wrong because it's a different expression. We do expect different expression. On every example that we've looked at, the expression for the inverse function is different, so we expect that it's a different equation. When we solve for y, right, we put it in a function form. The function form is a form that has the y as the output. So y equals what? 2/5 of x minus 3. So this is our original function. This is the inverse. Right? I just did some massaging to get from this one to this one. It's the same expression. Well, look, now we have the mechanism of how to actually get an inverse function if we have an equation of the forward one, right? So if we have the equation of the echo, we can figure out how to de-echo the signal that we have recorded. So let me just This, by the way, is a good example of a short clip that a student can repeat and see exactly how the building of this proof is done. Let me just repeat it as I would have recorded it. So I have a coordinate system that has the input side, which I call x, and output side, which I call y. I have a random function. I know what it means to be a function. I put an input on the x-axis, on the input side. I go up until it hits my function, my machine that will give me the output. I go left. This is the output. I know that from the definition of the inverse function, it is such a thing, it is such a machine that if I put this output into it, so I need to go to the input side, I will get my original number on the output. So I will get this. I have to copy this number there. Well, so what is the function? The function is such a thing that if I hit it, it will give me this number. This length is the same as this length. This length is the same as this length. So there is a symmetry. The coordinates of this point are in 1, out 1. Because of the way I drew it, I copied out 1 here as the x-coordinate. I copied this number there as the y-coordinate. So every point on the inverse function, if I flip its coordinates, it will satisfy the original function. It will be on the curve of the original function. That means that I flip x and y in the equation of the original function to get the equation of the inverse function. There you go. This is a 50-second clip that you can go forward and back and repeat until you have it. Also, here's a thing that I can use that is quite difficult to do otherwise. So for example, I can draw some function and demonstrate the symmetry. And here I'll just use 2x as the original function. So we already know that I just have to divide by the same number to get the inverse function. How can I show that it's symmetric? Well, I can draw it on the transparency and then I can go and actually flip it and see that it works. So I can take these two lines and do the actual flipping. Right? I can demonstrate the symmetry. This is difficult to do if you don't actually have this camera and the zoom and the transparency that it can flip. So this is a perfect example where asynchronous has the merits that are kind of hard to meet otherwise. So there you go. You can show it and imagine trying to show this for 20 students. You go around with this piece of paper and 19 students are waiting for you while you're showing it to the one that you're showing it to. Here, it's a one-on-one instruction and you have the mechanics that are very easy to actually implement. There you go. This is the end of the actual presentation. And now I just want to show something to be aware of. So what did we learn? What did we get for all the effort here? We actually got quite a bit. First of all, we got the fact that the inverse function is symmetric to the original function with respect to the reflection. So this function that we were studying here, if I draw the whole thing, it will look something like this. And so here is symmetry. Why is it nice to know that? Two reasons. One is if you actually have the original function or the inverse function, you can draw it with wet ink, and then you can fold your paper along the diagonal, and then you get the imprint of the inverse function, so you can actually get it very quickly. The working process is very easy if you know this. We figured out how to manipulate the algebraic expression for the function if you want to get the inverse. We flip the x and y, basically. What is this x and y? I think I should stop a little bit on this. So the function, what is the function? If you take y equals, for example, x squared plus 3 times x minus 7. So what we mean, the function is the machinery, right? It's taking to the second power. It's adding the expression that follows. It's multiplying by 3. It's subtracting the 7. So the things here are the machinery of the function. Right? This is machinery. This is the input. This is what I actually put into my machinery. And this is the output. So I flip the input and output and to put it in the same machinery to get me the formula. So I say x equals y squared plus 3y minus 7. But now, of course, I have to solve it to get the y as the output. And so this is a quadratic equation that I'll have to solve. I'm going to get square roots and such. There you go. We have a mechanism that we've learned, we've figured out just from the symmetry that again we got from the definition of the function. Because of the interesting quality of this symmetry, this is not some random thing. Here. There is only one line that is symmetric. There is only one curve, let's put it, that is symmetric about this rotation, about the diagonal. So there is only one inverse function. That's very interesting. This is kind of a pair of functions. One of them is inverse to the other, right? So if our forward function is the other one, the inverse is the first one. We can start here. If this is my forward function, this will be the inverse. If this is the forward function, this will be in the inverse. So they come in pairs. That's very interesting. And the last thing, of course, is that just from the picture, we now know that there are functions that are inverse to themselves. What does it mean? Something that has a symmetry in the function itself to this line. Some curve that for every point here has a point on this side. So a function like this. It has the symmetry built into it. So its inverse is actually the curve itself. I flip it and nothing is changed on my picture. For example, y equals 1 over x. The inverse, I know what to do in mechanics. I flip y and x. So this is forward. X equals 1 over y is the inverse. I put it in a nice form so that y is at the output. Look at this. It's the same expression. Yes, because this is the same curve. The function is symmetric to itself. The function is the inverse of itself. A function that looks like this, it's a circle that is centered on the axis of symmetry. Now, things to be aware of. Here's an example of an inverse function from the series on the Khan Academy website. How to get centigrade from Fahrenheit. This is the formula. Well, what is the inverse of it? Is if you have the temperature in centigrade, how to get Fahrenheit from it? What do they show you? They say, well, all we need to do is to rewrite it as what is the Fahrenheit as the function of centigrade. So multiply by 9/5 both sides. What are we going to get? F minus 32. So Fahrenheit is 9/5 times the temperature in centigrade plus 32. This is the correct formula, but this is absolutely the wrong way in the context of inverse functions, because it's the same expression. This is inequality that I just massaged to move things around. It's the same expression. We already know for all the examples we looked at that an inverse function in general is a different expression. And so this is what happened behind the scenes, is they've actually flipped the meaning of C and F, because here this is the input, this is the output. What is actually happening is this: y equals 5/9 x minus 32, and the inverse function, this becomes the output, y equals 9/5 x plus 32. Now they are different expressions, like we expect. You never in the asynchronous mode leave something behind the scenes, because there is a very high risk that it's going to be misunderstood and you're not there to catch it. So that's something I wanted to accentuate. And that concludes my presentation. This is the setup that I have used. It is actually very simple. So there's a camera on the tripod, there's a voice recorder, and it can be much simpler than this. You can also see that this is very homemade, so to speak. There is some glue tack here and scotch tape holding the tripod from tipping over. Any kind of camera works. The one that has manual focus is easier because it's not going to try to refocus when you have your hands under it. And these are just the papers and the printouts that I've prepared for it. So by no means is it free. It takes time to prepare. It takes time to rehearse. It will take time to remix the video if you want to, but if you're very good at presentation, you can do a through take and then you're done. So you can spend 15 minutes for a 15-minute video and post it on YouTube in another 15 minutes, and here is something that is multiplied by the number of students in your class, so the impact could be quite strong for something that is relatively easily done.